Today we will be going through a worked example of the complementary slackness theorem. Let X be the set of feasible solutions for the primal LP, x1 through to xn. Corresponding to X is the set of all slack variables, s1 through to sm. Let Y be the set of feasible solutions for the dual LP, y1 through to ym. Corresponding to Y is the set of all excess variables, e1 through to en. The complementary slackness theorem states that if X is the primal optimal solution and Y is the dual optimal solution, then Si times Yi is equal to 0 for I equals 1 through to m, and Ej times Xj is equal to 0 for j equals to 1 through to n. But how is this useful? Let's go through an example to understand how this theorem can be used in practice. Here is the primal LP we will be using for this worked example. Using the complementary slackness theorem, we will attempt to obtain the optimal dual solution without having to solve the dual LP. However, as part of solving for the optimal solution of the dual LP using the complementary slackness theorem, we will first need to know the dual LP in order to use it later for some simple substitution calculations. To calculate the dual LP, we first use the coefficients of x1, x2, and x3 in the primal constraints to form a matrix A, and transpose the matrix to form a matrix for the coefficients of y1, y2, y3, and y4 in the dual LP constraints. We add in the new constraints as per the matrix. Minimum becomes maximum. The right-hand side of the primal LP constraints become the coefficient for the dual LP objective function. The coefficients for the primal LP objective function become the right-hand side for the dual LP constraints. The constraint signs switch from greater than or equals to less than or equals to, disregarding the non-negativity constraints, and the non-negative constraints apply to y instead of x. We now have the dual LP, which we will come back to later. As a quick note, as this video is focusing on the complementary slackness theorem, this process has been explained quite briefly. For a stronger understanding of how to calculate the dual LP from the primal LP, I would advise you to supplement your learning with another video specific to that process. We will now solve the primal LP for the optimal solution using the simplex algorithm, a process which you should be fairly comfortable with by now. To do this, we add in our slack variables S1, S2, S3, and S4 for the primal LP and convert the problem into an initial tableau. Here are the results of the final tableau. Again, as we are focusing on the complementary slackness theorem, if you would like an understanding of how to obtain this final tableau from the initial tableau, I would advise you to supplement your learning with a video specific to the simplex algorithm. As such though, the optimal solution to our primal LP is S1 equals to 4, X2 equals to 4, S3 equals to 2, X3 equals to 2, X1 equals to 0, S2 equals to 0, and S4 equals to 0. Using the complementary slackness theorem, we can now use some simple substitution and basic mathematical knowledge to solve for some of the dual optimal solution and excess variables. S1 equals to 4. Therefore, since S1 is not equal to 0, for S1 times Y1 equals 0 to be true, Y1 equals 0. This is as for the multiple of any real non-zero number and another number to equal 0, the other number must be 0. The same follows for these three equations. We find that E2 equals 0, Y3 equals 0, and E3 equals 0. Now we can use the dual LP that we had calculated earlier. By introducing the excess variables, we can substitute all of the values we established before that were part of the dual LP. This is y1 equals 0, y3 equals 0, e2 equals 0, and e3 equals 0. For the two equations with only one unknown, we can perform some simple algebraic manipulation to find that y2 equals 2 and y4 equals 1. We now know that y1 equals 0, y2 equals 2, y3 equals 0, and y4 equals 1. The dual LP has now been solved for the optimal solution using the complementary slackness theorem.